Hi everyone. So thanks Marzena and Gediminas for inviting me to the workshop. It's really nice. And I'd like to also take this opportunity to congratulate everybody involved in this Quasimodo project. Congratulations on getting that. And so let's see, where's the slides moving thing? So let me start with an introduction to the introduction, in some sense. Oops. So what is this about with this weird title? So I hope most of you are familiar, at least a bit, with Bose-Bose quantum droplets, or quantum droplets generally, yeah? And so if you sort of think back, these are usually described from a theoretical point of view by the extended Gross-Pitevsky equation, or this extended Gross-Pitevsky Hamiltonian that we have here. And the essential part of that is this extra term called the Lee-Huang-Yang term, which is basically the quantum fluctuations of the ground state of the system, yeah? And then this leads to this extended GP equation with which you can do dynamics. And it's actually a remarkably good description of this system, and I think it underpins, I don't know, 99% of studies of these Bose-Bose droplets, yeah? However, I was always slightly displeased by this because there's this term, of course, here, and it's basically put in by hand because you look at the density of the equation of state of the system, and you basically say, yep, okay, so this term is going to be proportional to the density you have in a particular spot in your system. Let's just put it in by hand, and off we go. It works pretty well. But it uses this local density assumption that everything about the system is dependent on this instantaneous density. And so the thinking is, well, can we not do this? Can we just put the fluctuations in, which is supposed to be described by this term? And if we do this, can we, for example, see this droplet stick together because we put fluctuations in, which seems kind of magical. So I wanted to see something magical like this. Now, I have to thank Mariusz Gajda, who talked about quantum droplets yesterday, because he introduced the topic a lot, and so that will let me hopefully rush through this couple of the next slides. But of course, yeah, I'll mention a bit, because these Bose-Bose droplets are a bit different from the ones Mariusz was talking about, Bose-Fermi droplets. So, okay, we have the Hamiltonian with two components. Something weird's happening with this. Sorry. Sorry, it's a bit of a circus there with this. Yeah, so we have, I think it's still wrong somehow. Sorry. Okay, so we have two components, and they have the usual kinetic energy, self-interaction of each component, and interaction between the two components. And in the 3D droplets, at least, one assumes that this self-interaction is repulsive, and the interaction between component 1 and 2 is attractive. And the point being that if you write say the mean field Hamiltonian, you can rewrite it in this sense that you have kinetic energy, you have a term. It's just this stupid hair. Yeah. You can rewrite the Hamiltonian this way, in which there's a term here which is energetically not favorable when you have a low temperature. So you can, if you set up the interaction energies appropriately, you can be left with a small term which depends only on the difference between these coupling coefficients, like so. And in that case, you can have the densities should be, because of energetic reasons, they should be similar to each other. And then you're left with the delta G term here, which is small. And then the next order correction to the energy, which is this Lee-Huang-Yang term, can come in. That was a bit confusing, but let's continue. And so then this Lee-Huang-Yang energy comes from a summation of contributions from different plane wave states, at least if you take a local density approximation, that the little section of the gas that you're looking at is uniform. Yeah? And finally, what you get is this final dimensionless extended GP equation after scaling some densities and some units. Looks like this. The essential part of this is that we have an energy that depends on, if you like, the density squared, at least when the kinetic energy can be neglected locally. And you have basically a potential of energy density depending on the local density of your field. And there's a minimum at a certain density. And what this lets basically happen is that the system wants to have this preferred density, sort of like a liquid, yeah? And that's how you get this thing, a quantum liquid, a Bose-Bose droplet. And so then, for example, if you have some number of particles, what it wants to do is fill up, take most of these particles, put them in this bulk density, which is preferred by this sort of quasi-potential. And then as you put more particles in, you can start from a small droplet, which is basically mostly just composed of this skin, to once you add more and more particles in, you have bigger droplets with the same density. Yeah? And there's been experiments which have implemented this remarkably, and of course I have to mention the experiment in Barcelona, which was the first one that implemented these things. And there were also some important experiments in Florence with slightly different systems. And I also have to mention not an experiment, but a Monte Carlo simulation by Stefano Giorgini's group in Trento from 2024, where while we were mucking around with our attempt at doing this, they managed to do something somewhat similar using Monte Carlo, at least in a static sense. So this was great work there, where you can see the two colors. In this case, it was like in first quantized form, and these are the positions of particles in this Monte Carlo simulation, red and blue. Yeah. So continuing on, while that was in 3D, of course, since we're trying to do something experimental, it's much easier experimental numerically in 1D. So we have been looking at the 1D system, which was also described by a paper by Dima Petrov, like the 3D ones. He committed a paper a year later, where in 1D the droplet formation mechanism is similar to what happens in 3D, except strangely the Lee-Huang-Yang correction is negative in this case. So the Lee-Huang-Yang correction makes the energy lower. And so to produce a droplet, what you actually need is this remnant mean field interaction to be repulsive. So these two then fight with each other to make a sort of preferred density. And so yeah, this is now a 1D droplet here. As you add more particles, it becomes bigger, but keeps its density. All right. So yeah, coming back to what we wanted to do, we want to see if we can get the same effect with a raw wave function without this averaging, yeah? And for example, to see things like what Dima Petrov wrote in his original paper, he was saying that you can say that there's a long wavelength instability in the spectrum of this system, and that it gets cured by these quantum mechanical fluctuations. I'd like to see that, yeah. And of course, going to like a single realization, it's also helpful because, for example, we can see what goes on with correlations in the system, hopefully, which you can't with a mean field approach, or to see single shot behavior, which I'll show later. Maybe explain these discrepancies that were seen in the ICFO experiment, for example. Maybe, haven't done that yet, but that's sort of on the horizon. So here's the team, and these three guys here. It was mainly King here who was working on this, and also Maciej Kruk, who's here with us today, there he is, was working on this, and yeah, this guy. So our plan was the following. We can obviously do a Bogolubov description of this system, at least in a uniform case or in a non-uniform droplet case, and we can use that to generate a truncated Wigner ensemble of these cases. So each shot of the ensemble should be corresponding roughly to a shot of the experiment. And then we wanted to implement this, stick it there at time 0, run the dynamics, which is, in that case, basically just a Gross-Pateevsky equation, notably with no Lee-Huang-Yang term in there. It should be just sitting in the wave function, all that stuff, and then observe what it does. And how's time, if anybody knows? It depends how much blood and guts I can show. Lots of time. All right, so we decided to do this, and so try the simplest case, not actually going for the droplet yet, but just a single component Bose gas. Let's see if we can get this Lee-Huang-Yang term out of our system. And the results are quite bad if you just do this. Let me explain what's going on these plots. So imagine we want to do this numerically, so we have a numerical lattice for the system. It's not like a real optical lattice, but a numerical lattice to describe the field. And so that leads to a maximum momentum on the system related to the spacing of the numerical lattice, and a minimum momentum, L here, related to the size of the box. And then on this plot here, we have size of the box, or 1 on the size of the box, here. And here is the Lee-Huang-Yang energy that we get in this 1D system. And then all these lines here, they're for different numerical lattices. And so what can you say? We wanted to get this value. Remember, this Lee-Huang-Yang energy is negative. And what we get if we implement our little method and put into this truncated Wigner is these dotted lines here. So not only does it depend on the details of the lattice quite significantly, it also seems to diverge pretty strongly linearly from this number we want to get. And even though there's maybe an optimum set of parameters for this lattice that we have, it doesn't give a very good number. The discrepancy is maybe 20% or more, depending on the situation. And it's similar, but with different shapes if you go to 3D or 2D. Here's an example of, so here we have the momentum cutoff in the system. Here's what we expected for the Lee-Huang-Yang energy. A Bogolubov calculation would give this, which is maybe not so bad at high cutoff, although not ideal. But when we put it into this Wigner, we actually get these points. It's averaged over an ensemble. Pretty bad. It's like only half the value for no obvious reason. Depending on lattice parameters, it can be up here, down there. So, so while we're mucking around with this, Stefano Giorgini is making his Monte Carlo, for example. Yeah. So why is it so bad? There's a couple of reasons for this. One of them is that if you just look at the Bogolubov excitations in this system, and you just, implement them naively, add them up, the sum that you get is actually divergent in 1D and 2D at infrared, and in 2D and 3D in the ultraviolet. This is sort of well known that it's divergent. Yeah, you can see, so it depends on this KC. This is well known, and what's usually done to get the Lee-Huang-Yang expressions that people know is that there's a renormalization that's done on paper. Yeah, so you sort of do some stuff. You say that there's this Born correction, and then that gets into your coupling constant, so the one that you see in the experiment, and you think about, it's not actually the bare coupling constant, but it includes this dressed contribution. And then if you actually look at the Bogolubov, then the Lee-Huang-Yang correction is sort of infinite as you make the cutoff high, but then this Born correction is infinite with the opposite sign, and then you say, well, this is all inside the empirically observed coupling constant, so we put that in there, and we're left with a nice Lee-Huang-Yang correction. Yeah? But numerically, we can't do that, because if you add infinity and subtract infinity, you get this number that everybody likes in your simulations. That's a bit of a problem. And there's actually another reason. See, that problem I mentioned is responsible for this discrepancy here and this dependence on cutoff. But that doesn't even give us what we have in Wigner. And the reason for that is, maybe I have to step back here. No, I have to step forward, sorry. So when we implement Bogolubov, we take the Bose field, we put the condensate plus fluctuations, yeah? And then we churn it through and we discard high order terms. But when we put this into a truncated Wigner distribution, we can't discard high-order terms because it's all just one field. Like this fellow here becomes just a complex number field. So we can't untangle what was the condensate and what were the fluctuations. So when we put that into, for example, interaction energy, which has a fourth-order multiplication here, there's all these higher-order terms that are sitting in there as well, which we can't untangle. So there's contributions beyond Bogolubov, which obviously will not give us the same thing as if we had removed those terms. Fun and games. Maybe I'll skip past this. It's maybe not that important. So, in fact, if we look at the contributions in this numerical approach to the energy of this system, you can find that there's a whole zoo of stuff. So, for example, the stuff that's usually considered mean field consists of like a bare condensate contribution, G n naught squared times volume, plus a contribution from the fluctuations inside the density. So then you have G times n squared. And then there's in 3D, there's this contribution that's usually included as part of this Born correction. So then the actual mean field energy that one usually talks about that includes the Drest coupling constant is all this blue and purple stuff. Then there's the Lee-Huang-Yang term, which is this green part. And then in our case, there's also this ugly brown stuff that are some extra terms that correspond to cross terms from higher order contributions of the, if you like, the Bogolubov fluctuations interacting with each other. All that stuff. All right. What can we do? Well, the nice thing about numerics is that you can do numerical stuff. So rather than renormalizing on paper, we can renormalize in some sense numerically to get the energy density that we want, right? So what we do is we say, okay, we know from experiments or whatever that the coupling constant we need is G, so we want to set that, and the density we have is going to be N set, and so we can calculate that using, say, the Gross-Patayevsky mean field expression. That's what we want to get on the left-hand side, plus Lee-Huang-Yang energy, so that we can make droplets or whatever. And on the other hand, we can calculate the similar kind of stuff, but from the microscopic theory, the bare stuff, right, which includes the bare coupling constant, the condensate fraction, and some stuff about the lattice, which we can set. And so we can equate these guys and then do a numerical optimization. And then here we have the bare coupling constant for some case. The set coupling constant we wanted was 0.3 in this case, in whatever units. And so the total energy we wanted from mean field plus Lee-Huang-Yang was 180 something. And then this is the value we get from the microscopic Bogolubov theory, and you can see that there's a optimal value of about 0.27. And so you can iterate this a few times because you've still got this density in there and you want to get it all self-consistent. But it converges very nicely to some value, and we can use this. Or we can try to use this. So how does it go? So first, we're trying to get back what we put in. So here we have the lattice cutoff in the system. Here's the total energy. This is in 1D here. And so this was the mean field energy. The magenta line is what we want, including the Lee-Huang-Yang energy. And of course, from the ensemble, since it was optimized for this, we get these numerical data, the blue guys. And this is in 3D. So, okay, after much effort, for which King can vouch, we could get the right mean Lee-Huang-Yang energy in the system. What about other observables and things? Well, so for example, 1D, 2D, and 3D, here's what we sort of get for the optimal values of these bare coupling constants. G naught, for example, as a function of the lattice cutoff, and so you can see, if you can see these numbers, that it doesn't change much, but it does depend. So if you want to get these detailed things right, you have to do the optimization. For example, we can look at the local density-density correlation in the system, which is something that was not optimized for. And so you can see that it depends slightly on the lattice sort of features that you put into the system. For example, if you want to have good resolution, then obviously you want to have a high momentum cutoff to get those high frequency waves, and that'll depend a bit on that, but maybe it's not so bad, yeah? Dependencies of fairly small differences. You can look at the, for example, the split between interaction and kinetic energy, since we were optimizing for the total energy, including the ground state fluctuations, yeah? So you can see that, again, depending on these lattice parameters, there's a bit of a trade-off between how much of this energy that we should be getting is actually in the interaction and in the kinetic energy, but it's not a very big difference. The kinetic energy is really noisy because if you look at the guts of it, if you look at the momentum wave number of the system, and this is the kinetic energy density from a simulation. This is probably averaged over 10,000 shots or something like this. You can see that this high momentum part of the kinetic energy calculation is averaging to 0, but it's getting pretty noisy. That's why when the momentum cutoff gets big, you get a lot of noisiness in the energy calculation. All right, so how about some interesting things? So now we wanted to look at how this description of the system, this Wigner description, compares, for example, to this GPE description, extended GPE and the normal GPE. So this was a test case where you have initially a uniform gas with all this stuff included, and then we turn on a harmonic trap in this uniform gas. And so this is time along here, position, and initially it was uniform, and then of course you turn on a harmonic trap, and so it starts to focus. This is density, and so it focuses. There's like a high density phase of the whole business, which then gets washed out eventually. So comparing this is a single component gas, so the Lee-Huang-Yang effect in there is not so big. We're just sort of looking at what happens. There'll be like some preliminary droplet calculations later. So what can you see? The GP equation simulation here, it's not meant to form a droplet, it's just a gas in a trap. So it does whatever, and the eGPE does pretty much the same, right? If you look at the Wigner calculation, which includes more, what can you see? This is ensemble average. It's washed out compared to these guys, yeah? So both the GP and the extended GP, they're coherent theories, so they produce lots of these interferences here, not very big in this case, but they're visible. And of course, you can't see that in the Wigner because dephasing kills all those little interferences, yeah? You can look at for example, the density-density correlation here, which is not accessible using any Gross-Pateevsky type theory. And so you can see, for example, that it was coherent or slightly anti-bunched initially because of these quantum fluctuations. Then that gets worse, but then you have sort of, if you like, a better condensate forming transiently here, and then it sort of becomes more noisy. A second test case, we had some more, but these are the interesting ones. You can also start with a uniform gas, which is the easy thing to start with, and introduce a periodic potential, not a very strong one, into the system. And so, of course, yeah, it wants to concentrate in the minima of the potential you've introduced. And here you can see a fairly large difference, which is that both of these Gross-Pateevsky approaches produce lots of interference, fringes, and features. But then if you go for the more complete dynamics over here, that's all washed out very quickly. None of this sort of cross-hashing stuff here or these little features are actually true. It's all washed out. So that's, I think, one of the main take-home messages, that once you go beyond this extended GP approach, a lot of this coherent stuff that's fine is washed out. a question, so, okay, if you look here, you can think, is there any evidence that this extended GP is better than the plain GP in this case? It looks pretty much the same, yeah, and very different from this fuller theory. Well, you can try and have a look at this, and this is time for not this simulation, but this focusing one. So we have time, also here, and this is the density in the center of the cloud. With a couple of different calculations, there's a couple of different Wigner runs with different resolution on the lattice, and this GP and EGP. So, okay, you see that they're pretty much the same in many ways, but if you look in detail at the difference of this central density, the GPE, plain GP, gives, once it's subtracted, just 0. The extended GPE with this Lee-Huang-Yang term put in by hand gives whatever. And yes, you can see that this Wigner simulation does actually recover this small correction from the extended GPE in there. The only thing is that this is an average over lots of trajectories, maybe 10,000 or something like this. So you really, to recover this correction, you really have to average over a huge ensemble. You will never see anything in a single shot, because this noise will just be this big. Can one actually recover the extended GP behavior? Well, it all depends on, you see, like you're probably familiar with the fact that if you have a Gross-Piotr equation, there's a symmetry. You can make the coupling constant bigger by 10 times and the density smaller by 10 times, and you'll get the same Gross-Piotr equation. But it's not the same physics, right? There's actually less or more particles. And so indeed, if you make the coupling constant small, g, and the density high, then you get to a situation where all these beyond mean field corrections are much smaller relatively, yeah? And so these are single shots of these realizations. So it's this focusing case. And this was one with big coupling, small density. And you can actually see that there's these dark solitons forming in the condensate and lots of mess happening. Whereas if you go more to the mean field regime with small g, big density, that's mostly disappearing. It looks a lot like the ensemble average. This is maybe sort of obvious, but it's nice to see it happening. This is in K-space. Now, getting to the end, droplets. So having sort of recovered the fact that we can get the right density, can we get a Bose-Bose droplet in 1D? And so here's a starting condition. So this EGP mean field of the droplet is the red dotted line here, and these are the Wigner, one shot of the Wigner realization of the two components, component 1 and component 2. So you can see it starts with some noise on top of this EGP mean field. What's going to happen? Well, so here's the extended GP that we all know and love, and of course it's time, position, and we start with a droplet, and as it must, it's the ground state of that mean field Hamiltonian. It's stable. If we put it into a plain GPE with no Lee-Huang-Yang correction, then it just does this. It's not bound. So that's the control case. And if we put this Wigner distribution in with no Lee-Huang-Yang correction but fluctuations on there, Bob's your uncle, it sticks together. So it seems that, the first joy is that, yes, it turns out that you can put these fluctuations in, do nothing special by hand, and it sticks together for a while with lots of noisiness, yes? But you can get this droplet and try and start studying what's going on there. This is pretty recent results, so it's preliminary. You'll notice it's not in this archive that I was mentioning about the single component gas. And I'll just show a couple more slides about some of the dynamics that we see in this. So yeah, you can see that a droplet that lasts quite a while. It can also get sort of crappy, depending on such issues of whether, again, is it more a case of small g, large density, or big G, small density? You can see some sort of fragmentation maybe occurring. Some other typical cases are like this. This is actually a fairly typical case, which we want to try and understand but haven't yet. So you see, we start with a large droplet, and the first thing it does is it doesn't like the shape that it has. For some reason, it tends to self-focus. There's some reason we don't quite understand for this. And then it fluctuates around. It has defects inside it. It can split into two different droplets, at least in 1D. Or it can sort of peter out from the noise in the background. Sometimes the splitting can be quite nice into two large droplets, or maybe three in some case. And that's basically it. That's the end of the story so far. For me, the main thing is that yes, seeing is believing. You can actually put fluctuations onto this field, and they magically, in some sense, stick together into a droplet. I'm happy that it's possible to actually see that happening, because then you can try and start reasoning about what's going on and maybe how this coherent EGP description actually can break down. Yeah? It's much more noisy than at least we thought initially. And the outlook is we want to try and understand what's going on with this. Why this doesn't want to stay very nicely initially. Maybe there's something to be discovered there about the physics of these droplets. So thanks very much for your attention.
Okay, so it's 10:30, so a couple of short questions. Fogatti, Thomas?
Thank you, very interesting. Can I ask, it seemed in the droplet, you showed the initial state, and then you showed the noisy Wigner calculation, but you break the symmetry, right, of the densities between the two components slightly?
So in a sort of roughly what the difference is, that each point has a noise.
Yeah.
Or each point in K space has a noise, if you like. And yeah, that breaks symmetry, because the plus K is 10 has a different noise than minus K.
So is this the reason that you get this kind of complicated dynamics where the droplet doesn't want to stay together, you have lots of...
I'm sure it's a prerequisite for the complicated dynamics.
And these are single shot, or this is
single shots, yeah.
Okay.
Yeah, that's the thing. Yeah, I mean, this is probably happening because at least in 1D, this splitting, it doesn't cost a lot of energy to have a fluctuation come in, split your droplet into two bits, and then it doesn't have contact with each other anymore, presumably. Yeah.
Okay, thank you.
Okay, Ian Spielman. Yes. Thank you, Jakob.
Come back, is that okay?
Yeah.
So usually truncated Wigners, usually truncated Wigners only valid for short times, so I'm a little bit skeptical about these long time, hugely divergent
Yeah, I'm also
trajectories.
skeptical about this at long times. Yeah, it's one of the things we need to check out. So it's pretty good at short times. So I think, for example, this behavior here that it's focusing, I think that's legitimate. Whether this long time disappearance here is legitimate, that needs to be investigated. In particular, for example, look at different boxes and see if the disease that happens at long times, whether it's, does it get more serious with different box sizes, for example, in which case sort of a red light flashes, how much, then you need to try and see which things are sort of trustworthy and which are not. Yeah, that's right.
Okay, any more questions? Okay, Alessia?
So, thanks. But so for the moment, you haven't checked the excitation spectrum, right? Because
some preliminary stuff, but nothing that I could sort of say anything.
so, but you
good
expect
about.
that there will be changes with respect to Bogoliubov de Gen, or plus the correction, or
I think it should. I think the basic stuff in Bogoliubov de Gens should show up. Otherwise, that's highly suspicious. Yeah, but actually, we've done quite a lot of work, which I haven't shown, which Maciej Kruk, who's here, actually was worked on, which was non-zero temperature droplets using just the EGP, not this Wigner stuff. And there you can see a lot of the excitations from Bogoliubov de Gens. For example, you can see spontaneously produced surface modes going around droplets and stuff. Yeah. But it needs to be checked. It's one of these Outlook things.
Thanks.
Okay, the last chance to ask. So we all heard you presented a careful way how to stabilize 1D Bose-Bose droplet with no trap at all. Yes,
Sorry?
with no trap at all.
No trap.
Yes, and it stays self-bound
Yeah.
for some time.
Well, at least
Such
until
no-
there's Wigner disease, or maybe the noise kills it. Yeah.
Okay, so I think that after Piotr talk, we should all enjoy stable coffee droplets. So let's thank the speaker.